So, as we have spare time today, what I thought, since I noticed everyone's frantically looking at their exams and practice exams, we should probably use this time for exam review instead of lecturing. It'll take us a little bit more lecture time. We may have to lecture in lab to make up for this, but for today, we'll just do exam review in the exam.
Thank you.
Okay. So with that established, you're going to need to provide me some questions that we want to go over collectively. You're also welcome to split up into groups and choose questions that groups of you would like us to address. And we'll just address questions until the end of the period and work on problem solving. So is there any question from any of the material, be it an exam, homework, or practice exam that you'd like us to go over? Yes. Law of proportions question in the practice exam? Yeah. Okay, sure. So let's zoom into the intended question that's being covered. So let's look at a composition-based law of multiple proportions question. So, for those unfamiliar, law of multiple proportion questions will look at the composition of a compound. This is from our practice exam number 12. So when you read through the law of multiple proportion questions, your goal is to identify, first and foremost, what is the formula given, what are the masses of each element, and then which element mass is fixed. So let's write this out. So we have 8 grams of carbon. So we have 8 grams of carbon reacted with 2.66 grams of hydrogen. And in the end, we get 10.66 grams of carbon tetrahydride. So our first order of business is to take this name and get a formula out. So carbon tetrahydride, what 2 elements are present? Yep, so we see carbon, so we definitely have carbon. Tetra, so tetra. What does the tetra prefix tell us? 4. Yep. And then hydride tells us we have what element involved? Hydrogen. So it's CH4, also known as methane. Now, of course, by conservation of mass, you can figure out we have 10.66 grams. One thing that I would think about is just if I did not give you the mass of hydrogen, could you figure it out? Could you figure out the mass of hydrogen? If I only gave you the mass of carbon and the mass of our product, could you figure out the mass of hydrogen? Yes, because by conservation of mass, both of our input masses, the mass of our reactants, must match the match of our product. Notice how if you add these up, you get 10.66. Okay, perfect. Now let's look at our second experiment. So in our second experiment, we took 16 grams of carbon and reacted it with 2.66 grams of hydrogen. And in turn, we get 18.66 grams of an unknown compound. However, by looking at the masses of each element used in this reaction, we can relate the mass of each element used to the number of atoms in our product. So then, looking at this example, what mass does not change? Hydrogen. So hydrogen does not change. The mass of hydrogen used does not change. As a consequence for this, what remains fixed? If we have 4 atoms of hydrogen in our product in the first example, how many atoms of hydrogen will we have in our second? 4, exactly. Same mass, same number of atoms. So we definitely know it's of the form H4. Okay? Now what mass is changing? carbon, okay? Now, I like to handle things from a mathematical approach because that way it's very easy to see how changes in the mass of carbon reacted affects the number of carbon atoms. So in our first example, I have how many carbon atoms in my product? 1. So I have 1 carbon atom, and that 1 carbon atom is incorporated in our product from how many grams of carbon reacted? 8. Yeah, so per every 8 grams of carbon. Okay, in our second reaction, how many grams of carbon did we use? 16. So we multiply by 16 grams of carbon, and that leads to 2 carbon atoms. So that would give us the formula C2H4. If you stop there on the test, you'd be fine. Just from a purely technical perspective, since this method of determining a formula relies on mass ratios, we can't report a molecular formula. Instead, we have to report an empirical formula, which is the simplest ratio. So what's a smaller numerical ratio than 2 to 4? Yep, CH2, or 1 to 2. CH2 would also be a valid answer, and it's a more complete answer. Does that make sense to everyone? Okay.
Can we go for 13 as well?
13? Sure. So let's look at question 13 on the practice exam. I have it projected up front. It looks like a very tricky question, but it's fundamentally exactly the same. It's another law of multiple proportions question. So first and foremost, if we decompose a sample of copper to chloride, we make 25.38 grams of copper and 28.36 grams of chlorine, okay? I always am on the lookout for information that will allow me to write the formula. Can we write a formula for copper to chloride? Yes, and so it would be copper, what's the charge of copper? 2 plus. What's the charge of chloride? Just -1. We cross our charges, that gives us CuCl2, or copper to chloride. Always go through this intermediate work step. The last thing you want is to rush when writing the formula and then blunder the remainder of the question off of that. Okay, perfect. So I'm going to keep this formula off to the side. We'll leave it for later. Okay. In the first question, I want you to calculate the mass of chlorine per gram of copper. Okay? Do we have the mass of chlorine? Yes. Okay, so let's just plug that in. So we have 28.36 grams of chlorine. The reason why I'm writing it as chlorine atoms is it's a question regarding element composition rather than products of decomposition. Don't worry about that until chapter 4. It's mainly just this idea that in our sample, we have chloride ions, not chlorine molecules. Okay, we're then going to divide by the mass of copper. And what is our mass of copper in this case? Yep, 25.38. Okay, so all we have to do now is punch that into our calculator. Would you like me to show this on the document cam for the calculator input, or is this one straightforward enough that, okay. So we have 28.36 divided by 25.38, and that gives us 1.117 grams of chlorine per 1 gram of copper. So this is a mass-to-mass ratio. This is very useful in law of multiple proportion problems, and if you like solving these problems in a slightly different method, this mass-to-mass ratio is invaluable. I'm just getting you to think a little bit about the masses of each component element here to help us set up and see what is changing in this system. Okay, in the second case, we have another compound of the formula CuClX. I actually gave you excess information here because we see that it produces 25.38 grams of copper and 14.18 grams of chlorine. Would someone like to elaborate on my statement? Why did I say I didn't need to tell you that I didn't need to tell you there was one copper atom in this case? What's our dead giveaway that we have the same number of copper atoms? The formula, yes, but even if I got rid of the formula, is there a dead giveaway that we have the same mass of copper produced? Same mass of an element, same number of atoms incorporated into the product or as part of its composition. Okay, so in this case, we want the mass of chlorine per gram of copper for our unknown sample. Do we know that information? Is that all readily apparent? Okay, so we have 14.18 grams of chlorine per every 25.38 grams of copper. Now, this method of figuring out the formula using the law of multiple proportions, essentially leading you to this idea, the mass of copper is the same. So if we look at the ratio of the mass of chlorine, we can figure out the ratio of atoms. So this is another method that is showcased in this problem. So we have 14.18 divided by 25.38, and that gives us 0.5587 grams of chlorine per 1 gram of copper. Now, keep in mind, there's something implicit in the way I'm writing these answers. How many sig figs do all of my answers need to have? 4. So just be mindful, I am looking at sig figs. Okay, so our next goal is to write a formula for the unknown compound consistent with the law of multiple proportions. Okay, so first and foremost, we know our mass of copper is fixed, right? And in our first case, we have, so in our first formula, let's go all the way up here. In our first formula, we have how many chlorine atoms in copper 2 chloride? Well, how many do we see in this one? 2. Okay, perfect. So let's write that down. So we have 2 chlorine atoms, and that correlates to how many grams of chlorine reacted. How many grams of chlorine do we have in our copper 2 chloride sample? Yep, so we plug in 28.36. Now, in our second compound, how many grams of chlorine are found in our second compound? Yep, 14.18. Okay, the grams of chlorine cancel, and so we have 2 divided by 28.36 times 14.18, and that just gives us 1 chlorine atom. Okay, so writing out our formula, it would be CuCl, and then how many chlorines do we have? 1, so just CuCl. Now let's name this compound. Would someone like to propose a name for CuCl, a transition metal containing ionic compound? Yes. Yes, copper 1 chloride. Okay, and just to showcase the logic behind this, if we take our subscripts and we reverse cross them, we get copper plus and Cl minus. That matches the typical charge of chloride, so we're good to go. We read off the charge of copper, which is +1, so it's copper 1 chloride. Does that make sense? Okay. Any other questions that you'd like us to go over? This really is an open time. Yes?
I guess so polyatomic ions with hydrogen
yes.
are normally named with the hydrogen in front of it, and then
yes.
polyatomic ions.
Yes, and let me pull up another sheet. Okay, so let's talk a little bit about this. So polyatomic ions, let's zoom in. Just one moment. So in general, when you're naming hydrogen-containing polyatomic ions, such as, for example, HSO4 minus, So you precede the name with hydrogen. So you write hydrogen first. And then you write the name of the polyatomic ion. So in this case, SO4 2- would be
Sulfate.
sulfate. Exactly. So this is hydrogen sulfate. Okay. Let's try another example. So if we're dealing with H2BO3-, this is another one of your named polyatomic ions. This one's a bit of an odd one. Since we have two hydrogens in this case, how do we specify we have two hydrogens? Dihydrogen. So this is dihydrogen. And then what do we call BO3? Borate. Yep. Borate salts are principal agents of materials used to attract and kill ant colonies. You put the little puddle of it, and it traps the ants, and it's also poisonous to them. Okay, so again, you specify the number of hydrogens with the prefix. You write hydrogen in front, since it's a hydrogen-containing polyatomic ion, and then you write the name of your polyatomic ion. As we notice, one thing to keep in mind, if we think about borate, BO3 3- and H+. If we have two hydrogens associated, our total charge is -3 plus 2 times 1, which is -1. Each time you add a hydrogen, your charge increases and becomes more positive by 1 unit. Does that make sense? Okay, yes.
So how do we differentiate those from an oxy acid?
Ah, yes. So notice how for all of these polyatomic ions, they have what common feature? What common feature do all of these polyatomic ions have? A charge. Exactly, exactly, exactly. So for acids, they're neutral. And what that means is that they have no net charge. Does that make sense? So for example, let's look at the acid equivalent, which would be H2SO4. Again, no charge. This would be sulfuric acid. Does that make sense? Okay.
So, for example, if you were to, on an exam, have H2SO4 without the charge, you would just have to be like, okay, that's acid.
Yes, yes.
Whereas the polyatomic ion, which has that charge.
Yes. Or there's a corresponding metal ion. Yes.
Did you ever simplify that to like the H2SO4?
So,
2 on the 4.
No, because there's one sulfur. And when you're writing names for compounds and names for polyatomic ions, you do not simplify their formulas. You only simplify for empirical mass calculations. Yes.
So HNO3 would be an oxy acid, whereas
Yes.
H2NO3 would be just the first one.
H2NO3 doesn't actually exist. The way that you know the number of hydrogens that could be associated in the acid is you write out the charge of H+, you write out your charge of your polyatomic ion, which is nitrate, and then you cross the charges, and that gives us 1 hydrogen and a nitrate ion in the formula. So the charge of the polyatomic ion, in turn, indicates the number of maximum hydrogens found in the acid. Does that make sense? Perfect. Yes.
Can you go over the prefixes again, please?
Sure. Prefixes in what context? For
oxygen, like H.
yes. So polyatomic ion series. Okay. So let's do just that. So I'm gonna write out a few. So SO4 2-, SO3 2-. Let's do ClO4-, ClO3-, ClO2-, and ClO-. Okay. So The 8. So the ATE polyatomic ion is the most common. I like to think about it as the most common. So you memorize the 8 suffix. It's just the most commonly referred to polyatomic ion. Notice it's not correlated with the number of oxygens. It's not correlated with the charge. It's just for a series of polyatomic ions, the 8 is the most common. It's our reference point. Does that make sense? Now, depending on if we add an oxygen, we go from 8 to per prefix and then 8 suffix. So per 8 has the most oxygens. The per 8 species has the most oxygens for that polyatomic ion series. Does that make sense? Yeah. Now, if we reduce the number of oxygens, so if we lose 1 oxygen, we end up with the ite suffix, which has 1 less oxygen atom. So for example, looking at this series, we'd have chlorate, perchlorate, and chlorite. Notice how the prefix and suffix change when our number of oxygens change. Finally, if we lose an additional oxygen atom, we end up with the hypo prefix and the ite suffix. And the hypoite has the least oxygen atoms. So ClO minus would be hypochlorite. Does that make sense to everyone? Okay. So, just to make sure we're all on the same page, sulfate is SO4 2 minus. What would we call SO3? Sulfite. The reason being, it has 1 less oxygen, so it's sulfite. Does that make sense? Okay, any other questions I can address? Yes.
So in the notes, the chart was polyatomic ion had HSO4 5.
Yes, that's a colloquial name. You can use either the colloquial or the formal IUPAC name and you'll receive credit, though I'd recommend focusing on the IUPAC names as they're much more consistent and general. Yeah.
Can you explain a little bit more what you mean by that?
Oh, sure. So if we compare, for example, HSO4 minus, there are 2 possible names for HSO4 minus. The first of which is hydrogen sulfate. So this is your typical polyatomic ion naming convention for hydrogen-containing polyatomic ions. Historically, also, there are colloquial names. So if there's 1 hydrogen associated with a polyatomic ion, it's typically called bisulfate, where we have the bi prefix in place. Don't worry too much about the colloquial naming rules. It's better just to focus on IUPAC. It's why, for example, NaHCO3 is called sodium bicarbonate in some cases. While the correct name or the full name from IUPAC is sodium hydrogen carbonate. Yes, they both correspond to the same compound. They're just different naming conventions.
So would we be marked down if we use the colloquial name?
If it's the correct one, no. Yes.
Can we see an example of like a difference between a pure substance compound and heterogeneous mixture?
Sure. Okay, so we're asking the difference between a pure substance, a compound, and a homogeneous mixture. Well, that's easy. That's an example of a homogeneous mixture is the air that we breathe in this room around us. So thinking about this homogeneous mixture, in air, there is nitrogen, oxygen, carbon dioxide, and other volatile components. Now, as we can see, air, do we notice any separations, any phase boundaries, any inconsistencies in the composition of air throughout the room? No. So we can't distinguish between all of these pure substances found in the mixture. We can't physically see a separation in terms of chemical composition. If we're thinking about a pure substance, compounds by definition are pure substances. And the key criteria for a compound is they contain two or more different elements covalently bonded. So an example would be NO2. Now, one thing I do want to highlight is if we compare NO2 versus a mixture of nitrogen and oxygen gas, what is the critical distinction as well between a mixture and this compound, this pure substance? Are nitrogen and oxygen atoms covalent? Are the nitrogen and oxygen atoms bonded in our compound? Are they bonded in our mixture? Or is the nitrogen gas and oxygen gas, are they covalently associated? No. So in the case of a mixture, your components are not covalently bonded. Does that make sense? Perfect. And then a pure substance is either an element or a compound with fixed definite composition.
So like 1 to 1, or so like
As so like in NO2, for example, NO2 will always have 1 nitrogen and 2 oxygens. That ratio is always specific for that given compound. And that specific number of atoms is fixed. If you have that exact number of atoms covalently bonded together in that arrangement, you have that specific compound. Does that make sense? Perfect. Any other questions I can address?
can we do more, like, if you give us some practice on, like, let me rephrase that. Can we get more practice for questions similar to number 9 and 10?
9 and 10. Let me find that. Let's see. Nine and 10, you were saying? Sure, I can make a set. One moment, let me pull up that. Give me one moment, I'll pull it up for everyone to. Let me pull it up from one of your homework assignments and we'll take a look at a few of these problems. Just so that way it's a little bit more legible for everyone. And I'll have it pulled up in one moment. So we were asked to discuss iron 2 thiosulfate. Now, thiosulfate, whenever you have the thio prefix, that implies that we have replaced an oxygen atom with a sulfur. So the thio prefix says we've taken an oxygen atom and we've replaced it with a sulfur. So if we think about sulfate, it's SO4 2-. So thiosulfate, if we replace one of these oxygens with a sulfur, that would turn into what? S2O3. So we lost an oxygen, we've gained a sulfur. So thiosulfate is S2O3 2-. Now iron 2, our charge for iron is still 2+. We then cross our charges into our subscripts, and that in turn gives us Fe2 S2O3 2. And we can simplify this ratio to FeS2O3. There we go. Any other polyatomic ion pairings that you were working on? If you want, I can give you a few more minutes to take a look at this table and try writing out the formulas. Okay, and I'll be walking around and checking to see how everyone's doing.
Yes. Negative? Yeah, it is. It's a -2. Yeah. Okay, so CR. Okay. Yeah, I can't see that.
Oh, okay. Okay,
So that one's just gonna be the first Phosphate is a negative. Phosphate is a negative. Iodate is iodine. And that's gonna look like Fe5O3 yeah. Wait, Fe what? Do you get it?
Oh, no, I see. 1 pound is phosphate. Oh, a kilogram is 1,000. So this is phosphate.
Yeah, we got
0.2 times 1. It just so it's just this.
So are there any examples that we want to talk about as a group? This really is our time to review Any aspects of the nomenclature? And we'll also be doing some percent abundance problems later on. Yes.
Ruthenium sulfide?
Ruthenium sulfide. Okay, so the next example that we want to discuss as a class is ruthenium 3 sulfide. Okay, so let's process this example and let's switch to our, okay, so in this case we're dealing with ruthenium 3 sulfide. Okay, so let's start converting the names into actionable ions. Let's write the ions and their charges. So ruthenium 3, what's the charge of ruthenium? 3. So we write this as Ru plus 3. Now sulfide, not 8, sulfide, the IDE ending. What does the IDE ending symbolize? Is it an atomic or a polyatomic ion? Atomic, yep. So sulfide is S. So sulfur being a 6A element, what charge does sulfur prefer to adopt? 2 minus, yeah. 6 minus 8 gives us -2. So we cross our charges, and that in turn gives us Ru2S3, ruthenium 3 sulfide. Does that make sense to everyone? So would you like me to pull up some percent abundance examples now?
Yes.
Oh, one more? Yep, no problem.
For like oxalate?
Let's look at a specific example. So which compound would you want us to process? And try to pick one of the more complex ones.
Yeah, so I guess
Niobium, sure. So let's work together on the formula for niobium 5 oxalate, okay? So let's go and let's start transcribing these names into ion formulas. Niobium 5 oxalate. Okay, so first and foremost, we're going to write the symbol for niobium. And what is the charge of niobium given in this formula? 5. Yep, plus 5. Oxalate, what's the formula of oxalate? Yep, C2O4. And don't forget this critical aspect. What is the charge? 2 minus, exactly. So now we cross our charges. That gives us NB2C2O4 in parentheses 5. And there's no way to simplify this ratio further. Does that make sense? Are there any other topics that you want us to address? So if not, I'll be pulling up some problems on percent mass, if that's okay with everyone. Sorry, isotopic abundance. Let me get that pulled up. And a lot of the problem sets that I'm pulling up are directly from the homework. So let me pull that up. Give me approximately 2 minutes to do that. So in the following example, let's look at the information that we're given and what's requested in the problem. So we're given the isotopic abundance of rubidium 85, and we know that the remainder is rubidium 87. So this is a classic 2 isotope system. We're given the mass of rubidium 85 and 87. And we're asked to calculate the average atomic mass of rubidium. Okay, so let's color code our entries here. We know that the percentage of rubidium 85 is equal to 72.172%. We also know the mass of rubidium 85 is equal to 84.91179 AMU. Right? Those are the pieces of information given in the problem. Now, keeping in mind this information, we know that the percentage of rubidium 87 plus the percentage of rubidium 85 are equal to 100%. So then can we solve for the percentage of our other isotope? Yes. So the percentage of rubidium 87 is equal to 100% minus 72.172. And if we punch that into the calculator, we get a total of 27.828%. Everyone okay so far? Okay. We also know, erasing this equation as we've used it and we've extracted all of the useful portions that we can from it, the mass of rubidium 87 is equal to 86.90918 AMU. So from the data that we've assembled so far, we have enough information to calculate our average atomic mass. So let's do just that. The average atomic mass is equal to the percentage of isotope 1, which is 72.172%, divided by 100 times 84.91179 AMU, plus the percentage of isotope 2, which is 27.828 over 100, times 86.90918 AMU. Let's just make that AMU a little bit nicer to look at. Okay, perfect. Now all we have to do is enter this into our calculator. So let's Alt-Tab and let's go to our calculator interface. So this is where calculator errors arise typically. So here's what I'm going to do. First things first, what's the first thing that we have to input? What's the first operation are we inputting? Division, and then multiplication. I noticed that there should be a decimal point here. There we go. Okay. So let's enter 72.172 divided by 100 times 84.91179. And then we hit the equal sign. So this is what you get after the first step of calculations. Does that make sense? Now, you're going to hit the plus sign, and then you're going to hit the parentheses. And you need the parentheses here. If you forget that, you're going to end up with the wrong answer. Then we're going to enter this next string of inputs. 27.828 over 100 times 86.909. Does that make sense? So let's punch that into our calculator. So we have 27.828 divided by 100 times 86.90918. And in the end, we get a grand total of 85.4676. So our mass average, our average atomic mass is 85.46762. Now, we're going to have to round our result. We're going to have to round our result. And what is the least number of sig figs present in this computation?
5.
Yep, 5. So we're going to round our answer to 5 sig figs. So we end up with 85.468 AMU. Does that make sense, Sarah? Okay. Would you like to do another example in isotopic abundance, or is there another topic that you would like us to address? This really is open time.
Can we do one more like this?
Sure, sure. But let me try to find one that's a little bit more difficult. So I'm going to pause our... So let's just highlight what is being asked in this problem. Really just focus on what is being asked of me in this problem. So we're asked to determine the atomic mass of neon-22. Okay, so we want the mass of a specific isotope. Okay, so what we're going to do now is we're going to write out all of the data that we know. We're going to write out all of the data that we know and all of the data that we can get. The problems are not going to tell you where you can potentially get the data. You as a chemist will have to know, where can I find information relevant to this problem? And first and foremost, we're given the mass of neon 20 is 19.9924 AMU. We know that the percentage of neon 20 is 90.483%. Okay? We know that for neon 21, the mass is equal to 20.9938 AMU, and the percentage is equal to 0.271. Finally, do we know the mass of neon 22? Do we know the mass of neon 22? No. So I'm going to write this as just a question mark. Can I figure out the percentage of neon 22? If all of these percentages need to add up to 100, can I figure out the percentage of neon 22? Yes. So by subtraction, I'm going to take 100 minus 90.483 minus 0.271, and that gives you 9.246%. Okay, so we have a ton of information here, and as the cherry on top, what's one other piece of information you always are expected to have access to if I give you a periodic table? The average atomic mass. So let's show where we're going to get that, because this is going to be really important when you take your exam. Whoops, one moment. So the average atomic mass is found in the periodic table as the mass number. So if you're going to your exam periodic table and going all the way to the top, lo and behold, we see under neon, what is our average atomic mass, roughly? 20.18. I'll not tell you that you can look at the periodic table, but if you're given a periodic table, you should use it. So our average atomic mass is 20.18 AMU. Does that make sense where we're getting all of this information? Okay, we're next going to write out our average atomic mass equation. So our average atomic mass, which is 20.18 AMU, is equal to the mass of isotope 1, which is 19.9924 AMU, times the percentage, which is 90.483%, divided by 100. We're then going to add the mass of neon 21, which is 20.9938 AMU, times the percent abundance, which is 0.271, divided by 100. And I'm going to have to zoom out because this formula string is quite long. Finally, we have the abundance of neon 22, which is 9.246 divided by 100, times the mass, which is, I'm going to call X. So all I have to do is solve for X, right? This is just turning into algebra. So to make things a little bit easier, I'm going to convert anything I can into a number, okay? So let's start by processing this expression in blue. Let's process the expression in blue. So we're going to hit 19.9924 times 90.483 divided by 100. And that in turn gives us 18.089 AMU. Can we process the expression in red, or is that all numbers? Do we only see numbers in red? Yep, so we can do that. Okay, so we have 20.9938 times 0.271 divided by 100. And that in turn gives us 0.05689 AMU. I'm over retaining sig figs just to cover my bases here. Okay, now with this established, we can now move all of our numbers. We can move all of our numbers to the left-hand side. So we're going to subtract all of our numbers. Does that make sense? Okay. So I'm going to do that really quickly. So I'm going to take 20.18 minus 18.089 minus 0.05689. And that in turn gives us 2.0341. Don't worry, we will truncate sig figs in a moment. Just as a side note, we're retaining up to the second decimal place because we did a subtraction operation and this number has 2 decimal places. Does that make sense? Okay, now let's include our portion in blue. It was always present, but we weren't really focusing on it now. Because now that we have all of our constants on the left-hand side, can we solve for x from this point? Can we solve for x from this point? Okay, perfect. So what we're going to do to solve for x is we're going to multiply by 100 over 9.246. And that in turn gives us a value of x. So we have 2.0341 times 100 divided by 9.246. And in the end, we get a mass of 21.997 AMU that we round up to 22.00 AMU, which matches our expectations, right? Neon 22 should have a mass eerily close to 22. Does that make sense to everyone? Okay. Any other problems that you'd like us to go over as a class? Any other topics that you'd like us to address as a class? Yes.
I thought I heard someone say they wanted a conversion.
Conversions? Yes, I can pull that up. About this example. So we're going to address this example on a separate sheet. So let's make a new page and let's write out our given information. So reading off from the problem, I'm going to need everyone to help me out on this. Do we know the mass and density of the Earth? Yes. So let's now take a look. So the mass is equal to what? What is the mass of our Earth equal to? 6.0 times 10 to the 27th. Okay, grams. Always make sure to write the units. Our density is what? 5.5 gram per centimeter cubed. Perfect. Okay, so we have this information. Now, in the end, the problem is asking for the volume in liters and kilometer cubed. So 2 different unit outputs, okay? So let's tackle this step by step. We're going to do liters first because it's by far the easiest. So from my perspective in unit analysis, I want to end up with units of liters, and I am starting with units of grams, right? That's what I am given. This is where I want to go. Do I have a tool that allows me to go from units of mass to units of volume? And what units of volume can I get using this density up here? Yep, so I can go from grams to centimeter cubed. Can I go from centimeter cubed to something related to liters? What was that? Milliliters, exactly. Because remember, 1 centimeter cubed is 1 milliliter. Okay, with all of this information established in my solution map, all I need to do is write out my answer. So I have 6.0 times 10 to the 27th gram. Now, if I want to go from grams to centimeter cubed, what units need to be on top? If I'm going to centimeter cubed, what do I need on top? Centimeter cubed. So I set this up where I have 1 centimeter cubed per every 5.5 grams. Does everyone see how I used density as a conversion factor? Just like you do for any unit conversion. You set up your starting unit to cancel, and you have your desired unit on top, or wherever you want your desired unit to be. So grams cancel, perfect. I'm going to set this up as a one-line conversion because there's no reason to not just write out all of my conversion factors. If I'm going from centimeter cubed to milliliter, what goes on top? Milliliter. So we have 1 milliliter per how many centimeter cubed? 1. Now, the last portion of our conversion requires us to remember metric to metric conversions. So if I'm going from milliliter to liter, what goes on top? Liter. So I have liters over milliliters. I put my number with the prefix unit. 1 always goes with your prefix unit, and then your power of 10 goes with the base unit. And 1 milliliter, what does the milli prefix correspond to? Yep, 10 to the negative third. Not too bad, right? Remember, any problem in chemistry can be solved by proper application of unit analysis. You look at your starting units, you look at your ending units, and you make a solution map to go from your starting to ending units. This is a fundamental skill that you will need for later chapters. So if you're having difficulty with these types of conversions, you really want to practice them because that's all we're going to be doing for the next, till the end of the semester, basically. So let's now punch this into our calculator really quickly. So we have 6.0 EE27 divided by 5.5. We'll end up with a large number. If you see a really small number for the volume of the Earth, just make sure you do a little bit of a reality check. The Earth is definitely going to be larger than a milliliter, right? Hopefully we can arrive at that conclusion. And now we're just going to multiply by 1 EE negative 3, and we get the Earth's volume to be equal to 1.09 times 10 to the 24th liters, which we round to 1.1 times 10 to the 24th liters. Does that make sense? Now, oh yes.
Do that again.
Oh, sure. So we have 6.0 EE27 divided by 5.5 and then times 1 EE negative 3. And that gives us 1.1 times 10 to the 24th. Does that match?
Yeah.
Perfect. Now, one last thing. Oh, we're out of time for today. So we'll have to break and get ready for our exam.